Thank you guys for joining today. Today's webinar topic will be spacecraft thermal and propulsion control with CAE and system simulation. My name is Mason. I am from AT Engineering. I'm based off in the San Diego office, and I'm very happy to be joined by Stefan from Siemens today. He is a subject matter expert of Amesim, Simcenter 3D, and he will be the one presenting the topic. Just before we dive into the webinar, just a few housekeeping notes. All attendees will be muted throughout the webinar. If you have any questions, feel free to type them into the chat box, and we'll answer them at the end of the presentation. And you will also be able to ask the question directly if you like, and we'll just unmute you at the end of the webinar. This webinar will be recorded and will be available on our website and our YouTube channel later on. And before I hand this to Stefan, I wanted to give a quick overview of AT Engineering, about who we are and how we might be able to support your team. So most people recognize ATA as an engineering service company, and our core founder have actually been working together for almost 40 years. And we have vast experience providing high-value engineering services focused on test and analysis-driven design. Majority of our business are in aerospace and defense. That's about 70%. But we also have work on other industry, as you can see on the right. A little bit about who we are. We are a employee-owned small business with a full-time staff engineer, just over 200 people. Most of them have advanced engineering degree, as you can see on the right. We have 7 regional offices across the US. Soon we'll have the 8th one. And as I have mentioned before, we have years of experience focusing on design, analysis, and tests. This includes everything from, let's say, structural design, dynamics, thermal analysis, CFD, and more. And test-wise, we are the leading independent model test group in the US. We have lots and lots of experience flying our team to the testing article location and just conduct GBT and use that information to help drive the model design. So aside from our engineering service business, this is how most of you joining the webinar today know about AT Engineering. We are Siemens VAR, value-added reseller, who do not only sell the product, but also provide software support and training to our customers. So we really focus on products like that helps design, analysis, and tests. For example, NX is a leading CAD software that used for modeling, VMAP, Star CCM Plus, and Amesim, which is the topic for today, is for simulation. And for test, we are the sole Siemens partner in the US providing the testing hardware and software. So because we sell what we use, our customer really appreciate our familiarity of these tools and really shows in our hotline support, which every time they call, they are speaking with engineers who actually use and know the software. In addition, we teach a variety of classes, primarily dealing with simulation like Nastran, VMAP, and more. So this is a newly added slide. I think it'll be interesting to talk about AT Engineering and Siemens kind of history. So it all started out for a company called SDRC, which they created a tool called Ideas tool, and later got acquired by Unigraphics, and later on become the well-known NX product. And AT Engineering, it's a company that spun off from SDRC starting in 2000. And we have lots and lots of experience using the software, using Siemens software, and eventually we became one of Siemens VAR in 2016. And then later on, our partnership became stronger, and then we became the gold partner, and then became the platinum partner, and eventually we're hosting a lot of seminars and training events for Siemens. All right, last slide for AT Engineering. We have a page on our website that you can get free resources and product information. I encourage people to go online and check it out, including APIs, white papers. All right, so let me give a quick introduction of Amesim and kind of this for the space industry, and then I'll give that to Stefan for the integrated approach on his slide deck. So let's talk about some current challenges for space industry. This includes like new legislations, increased payload and launch frequencies, electronics integrations in severe environment, and just secure and shortened spacecraft system integration in an extended enterprise. This includes OEM and supply chain. So what Amesim's value proposition is that, let's say for a spacecraft launcher, these are all the capabilities that the Simcenter portfolio can do, but on the highlighted text of blue text will be the one that Amesim is really good at. So like, for example, under propulsion systems, cryogenic system analysis, flight controls and actuations, and for today, more towards today's topic of satellites, under satellite structure, the thermal systems or like propulsion systems. And for missile development, same thing for thermal, so for ejection and launch installations. And you can see Amesim is really good at modeling those systems. So where does Amesim sit in the Siemens Simcenter portfolio? So this on the left is the Simcenter portfolio of Siemens. As you can see, it has different domains like mechanical, fluid and thermal, electronics, physical testing, and systems. So mechanical will be the one that you're most like FEAs, like Simcenter 3D, VMAP, Nastran, but Amesim is more toward the system domain, which it's designed for mechatronic system performance, and from like early age development stages to the final performance validation. So what Amesim really is a system simulation platform that allows like engineers to virtually assess and optimize the mechatronic systems performance. So it boosts overall system engineering productivity from the early development stage to validations and calibrations. So one of the big things for Amesim is that it has a ready-to-use multi-physics libraries that combines with application and solutions supported by the platform, which you can see over here. Oh, actually, I think I took that slide out. Yeah, so basically you can use those libraries to build up your 1D systems and kind of simulate those and get an idea of what that actually is. All right, so that's a quick intro of Amesim, and now I'll hand it over to Stefan. So take it away.
Thank you, Mason. Hello, everyone. Very pleased to join this webinar from ATA. Just give me 1 minute. I will share my screen. Okay. Thank you, Mason. Yeah, so as Mason presented to you, this is the agenda of our today webinar. So the first topic that I will address deals with the thermal management of a satellite, so using a vapor cycle systems. And in a second part, I will illustrate a hypergolic liquid rocket engine. So basically, two different engineering tasks, but leveraging the same ideas, the same methodology to deliver better design using system simulation and our system simulation solution, namely Simcenter Amesim. Yeah, so a mechanical heat pump is a machine, okay, that can remove heat from one location and transfer it to those another location, so requiring heating. And traditionally, the cooling of a satellite electronics was done using capillary pump loop heat pipes. And these pipes are used to transfer the heat from electrical components to large radiators. But recently, with the need to have more and more electronics on board and also to reject more heat, mechanically pumped systems are investigated. and they have some advantages over the capillary-based heat pipes. We can mention the fact that they can transport more heat over a long distance because they are less sensible to pressure drops, contrary to capillary-based systems. They are much more easy to control. They are much more robust during startup phases. And designers access more freedom in terms of orientation versus the gravity. And so the advantage of Viper cycle systems are, on one hand, high heat exchange and stable temperature control, so during the phase change, and on the other hand, flow can be controlled to produce an effective heat dissipation. Our Simcenter system simulation, so AMSIM, allow us to simulate dynamic multiphysics mechatronic systems, as Mason introduced it. I will show a bit more in a minute during a live demo. So the design of the fluid loop is based on available database of refrigerant that we can offer. And also we use some requirements for power dissipation and the temperature we want to maintain in order to do the static sizing of the loop. And then we can reuse the model to study transient phenomena and study, for instance, the impact of heat load variation. And also I will show how we can test some pump control strategy to reach, for example, a target temperatures. Okay, so let me just now switch to Amesim. Okay, I think you see here my screen. This is the graphical user interface of Amesim. Basically, we have 4 different modes in order to build our model. We have a sketch mode, and in this sketch mode, we access different kind of library that Mason mentioned in his introduction for the different physics, mechanical, fluid, thermal, electrical, and also two-phase flow, which helps to model HVAC or vapor cycle systems. Okay, so I'm displaying here the two-phase flow library, and you see that the library offers different component categories, which are referred here on the right side of the screen: sources, fluid node volumes, different frictions, pipe, control valve, different turbo machine, compressor, turbine, pumps, heat exchange, specific component to handle the moisture, and also some specific subset of components which allow to model linear actuators that we call component design. And before doing the assembly of the sketch of the Viper cycle system that you see here, at Siemens, we also developed solutions which address all the levels of modeling, including the first round of calculation, so at very early stage of the design. And in this context, we propose an app space that I'm displaying here, in which you can find different apps, and one is dedicated to thermodynamic cycle analysis. And this is one which is currently open here. And this helps you first to select the fluid you want for your refrigerant system. So you see that we have a database with different available type of fluid and refrigerants that you can pick and select. You can even potentially define a mixture of those refrigerants. And once it's done, so you follow the tabs, you can start to define your cycle. Okay, I will start to increase a bit the size of this window. And you see that you can start to specify the different transformation of your cycle. And so for my system, I have the pumping, the evaporations, the expansion, and the condensations of the cycle. And you see that for each transformation, I have some settings that I can use to specify inlet and outlet conditions. I have different options. I can specify pressure, temperature, or pressure enthalpy, or temperature and gas mass fractions. I can specify value, but I can also, for instance, like for the pump, specify some gradient. I can specify the pressure increase of my pump, so 0.25 bar, or I can directly here give the outlet pressure of the pump. I also specify here a isentropic ideal transformation. I put one. And let's make a zoom. I start to define the green segment, and you have here the transformation data, so the inlet and outlet state of the fluid with the different interesting information that I define on the left, but the fluid properties also allows me to retrieve other information. So for example, here I specify a pressure enthalpy, and AMSIM is computing the temperature, the density for the inlet state, the subcooling or the superheating, the gas mass fraction, and so on. So I'm doing that for all the different transformations. Of course, from the evaporation, I can refer the inlet as the outlet of the pump. Okay, so no need to define twice the same point. And once it's done, I have a recap of the cycle data for each of the transformation, a recapitulation of the different pressure gradient, temperature gradient, also the mass flow rate and the power. And this is something that I can specify, for example, at the pump level. I can, for example, directly specify a mass flow rate, or alternatively, I can specify a user-defined power. And in this case, you see for the specified power, MSIM's computing the corresponding mass flow rate I need to represent the thermodynamic cycle I specify. And once it's done, I won't do it right now, but you can create the sketch, so you can keep all the information of the transformation data and export it. So I will close now this window. So of course, I did not comment, but you have diagram representation. Here I use the pressure enthalpy, but you can also access other diagram display to check what is the shape of your current cycle. And once you're fine with your specification, you can click on create the sketch, and it automatically create those boundary conditions which will be kept to be used as a reference information for my for the sizing of my loop. And now you're ready to build the sketch with the different pieces of equipment. So here I have a pump, and for my pump, I start to specify the volumetric displacement. I give also the different efficiencies. I give the rotational speed, and I continue also to describe and discretize the different heat exchanger like the evaporator. And so I discretize my evaporator into 5 different pipes. For each, I define a geometry, a pressure drops, a heat exchange. And you see that sometimes, rather than to give numerical value, I have defined what I call a global parameter. And when a parameter needs to be referenced at different location in your model, you can keep in one place. So in this global parameter setup window, you can keep this value and assign them, for example, to the different pipes in my system. And each time I'm selecting a value, it displays the pipe, for instance, which owns the same area, the same diameter, the same length, the same roughness, and so on. So you define and you size your systems, and you can perform first simulations. And when you run it, so you have some run simulations. There is then a computation which is done by our solver and which integrate the different equations which are related to the different component of my systems. And for each component, you see that you can access different variables. So I can drag and drop all the temporal evolution of those, we call this variable state or simulation results. Okay. And here I already predefined the plots. And this is a thermodynamic plot that you can define, which allow to plot in a pressure enthalpy diagram the result of the simulation that you see in red, and you can compare with the experimental result, because for this model, I refer to some technical paper with some experimental result, and this is the one I use to define my thermodynamic cycle, and I can compare how good is my static sizing for my systems. Of course, there are some difference because with the different pipes, for instance, I introduce some pressure drops. So you have some pressure decrease for my systems. So the system is not ideal like I define it, but still it match quite well, I would say, the different points I define. And once you've done that, you can start to look at what are the dynamic performances, because yes, the dynamics matters. The static approach is not enough. And when you want to see the impact of changing the load variation, so you see that I specify some heat load of my electronic pieces of equipment as a boundary condition. I want to assess what happens when I change that. I make it evolve over the time. And for that, I created the second model. So I reused the static model, and I just introduce variation of my heat load, so that at a certain point on time, after 250 seconds, I increase the heat load by 200 watts for the evaporators. And I want to study also the control of the pump. And so in order to increase the heat exchange, not increasing the temperature inside my evaporator, I can adapt the amount of flow rate produced by the pump. And this is exactly what I'm doing here. So I defined a temperature target of 90 degrees, and I use a PID controller in order to regulate the mass flow of the pump in order to, I would say, address this new boundary condition change. And when you run simulations, again, you can plot and display evolution in a pH diagram. And so for the first 250 seconds, you see that the heat load is the 600 watts, so it's similar to my static condition. And at some point, I increase the load to 800 watts, and I see how the cycle loop reacts to that. And I can also look more precisely at the temporal evolution of the temperature at the different place in the evaporator. And I can also check, for example, along the evaporator, what are the evolution, for example, of the gas mass fractions. So I can retrieve this information among all the simulation result I have. And you see, and you can look at the evolution of the gas mass fraction inside my evaporators when the condition change. So you see this decrease at 250 seconds. Okay, so this is how the 1D system simulation takes place. That's good, but what about the interaction between this mechanically pump loop and the surrounding? Okay, the mechanical pump loop is mounted on a satellite and has a complex layout. It's made of multiple equipment with different materials in contact or not. So you might have some multi-layer insulation. There is also a need for advanced radiation analysis to account for a series of emitting and reflecting surfaces that see each other. Also, you might have some part of satellite articulated, like solar panels, deployable radiators, tracking antenna, and so on. And you may have also to account for the spinning of the components. And this is where the Simcenter 3D technology comes to rescue. And so in our Simcenter 3D technology, we have a special functionality which is built on top of it, which is a thermal solver technology called 3D Space System Thermal Solution. And this is a key functionality for space application when you have to address radiation modeling inside enclosure, as we have for our systems. And it's possible to perform a co-simulation of space vehicles and equipment using the Simcenter 3D and the Simcenter system simulation solver, namely Simcenter Amesim. And with that, you can account for model orbits, space environment, and transfer their effect to the 1D solver. And this is exactly what we've done for the use case. So yeah, you can see animation of the Simcenter 3D. And for use case, we proceed to a geometrical discretization of the condenser and the evaporator coils, and we perform co-simulation. So on Simcenter Amesim side, like I show you, we discretize into 5 different pipes for each coil of the, for example, the condenser shown here. And on the 3D side, we define one thermal convective zone, which is displayed here for each coil, and we perform co-simulations. And we enable so a direct communication exchange between Amesim and Simcenter Thermal Multiphysics. So Amesim receive from the 3D environment a solid temperature and compute a read flow rate that is sent back to the 3D solver. And this avoids, I would say, some error, which are traditionally introduced when you traditionally use data sharing using file exchange. So when you do manual multiple iteration to converge, so it's also help also to capturing some 3D dimensional heat transfer in the Amesim model. So it helps to improve the accuracy and finally refine the sizing of the system model. And it gives also to the 3D simulation a more realistic boundary conditions and also give some fast simulation computation for the two-phase fluid part, which is computed by the system simulation, which is fast computing. And so with my colleague Florian Sanchez, who helped me to prepare those slide deck, we perform and we use those co-simulation between 3D and system simulation on a reference use case that is mentioned here. And you can see here some snapshot of the result we obtain. Like, for example, the fluid temperature profile in the evaporator. And you see here from the 3D side the gradient. You can see also from the system simulation side the phase change of the fluid, which is similar to experimental data. And with this use case and proof of concept, we validated, I would say, the co-simulation framework we implemented for our systems. Okay, this is this was the end of the first part of my presentation, and I will start to present the second part, which deals with the Aegis engine storable propulsion systems. Maybe I will take the question at the end of the presentation if you have. So I will present now a model we developed also about this rocket engine demo model. So in our product, we have what we call a demo portal. So you can download and access a set of 5 demos that show you a step-by-step approach in order to build such a storable propellant stage system. We, I would say, get some data from available public literature of the upper stage of the Ariane 5 launcher. So this stage propels the payload to its final orbit and provides the necessary thrust. And this stage is equipped with the so-called Aegis engine, which is fueled by monomethyl hydrazine and an oxidizer. Oxidizer being either nitrogen tetroxide or peroxide. And helium is used to pressurize the propellant tanks. Okay, so now I will tell you more about this pressure-fed engine cycle. So I will describe separately the following subsystems. So first, the combustion chamber, the nozzle, and the regenerative circuit. Then I will talk about the fuel pressure valve assembly. I will have then a word on the helium pressure regulator, and then the propellant tanks. And at last, I will come back to Amesim and show you the global integrated model. So let's focus on the rocket engine as shown in this picture. So the model has been set up and calibrated in comparison with test or specification that we, as I said before, found as public information and inside the literatures. And this model is composed of 2 parts. On the left parts, we start to define the fluid properties. We also import some data from the literatures, and we define also some control of the valve, so to let fuel and oxidizer flow into the systems. In this model, we use some variable orifices. They don't represent the actual control valve. I will show you after the model of the control valve. They are just here used to connect with the pressure temperature source of the engine that we use to somehow calibrate our rocket engine. And in the middle part of the sketch is the engine itself. So you have the combustion chamber, you have the nozzle, and you have the regenerative circuit, which use the fuel to cool down the nozzle. Here is the fuel pressure valve assembly, which are used to feed the combustion chamber with constant and controlled flow rates. And for both the fuel and the oxidizer, the valves are identical in terms of architectures, even if they differ in detailed design parameters, like the diameters, the spring stiffness, the flowing area, and so on, because it's obvious that the propellants have different fluid properties, so the design has to be adapted to the different densities and viscosities of the fuel and the oxidizer. And so you see here on the right the fuel valve architectures. And this assembly is composed of 2 electronically controlled pneumatic valves and 2 pneumatically controlled valves, ensuring the fuel metering from the tanks to the combustion chamber. And in these systems, in the Amesim model, so we start to define the pneumatic pressure sources, so the low pressure sources and the high pressure representing the helium pressure. So helium pressure is directly controlled by a pressure regulator located downstream the helium tank, and I will show you afterwards the modeling of those valves. Here, the boundary condition in terms of pneumatic pressure, but also in terms of combustor chamber pressure have been set up using the test data that you see on the left here. And once the pressurization of the propellant tank is done, the first electronic valve is open, which then releases the first pneumatic valve. Then the second valve is operating. This is the fuel metering unit assembly. Okay, and you see the correspondence between the sketch and between the Amesim model, and I think you can easily recognize, I would say, the correspondence between the electronic and pneumatic valve. And for that, in our Simcenter Amesim environment, we use special mechanical, pneumatic, and thermal hydraulic detailed design component library to make the assembly of the valve in order to produce a predicting dynamic behavior of the valve model. And this allows then to dose the fuel mass flow rate, which is sent to the combustion chamber. And thanks to the test data, we calibrated parameter of those valves, actually the frictions and also the geometrical parameter in order to match the test data. In the same approach, we use the same approach for the helium pressure regulators. These pressure regulators plays a critical role in the pressurization process. And the parameter of this regulator have a significant impact on the rest of the system and also impact their dynamics. And the dynamics is influenced by the propellant and the helium tank pressure. And so due to the wide range of pressure of the helium, so from 400 to 60 bar, a single pressure regulator is not sufficient. So that's why we have a two-stage regulator to have a more precise control. And so on the right, you see the helium tanks, which have been represented with some pneumatic capacities for a total mass of helium of around 34 kilogram, and the initial pressure around 400 bars. We have then some filter and pyrotechnics valve, which are represented with orifices in order to account for the pressure losses. The pyro valve is normally open and never change its state during the simulation. And then we had done a careful sizing again of the geometry of the different pressure regulators. So adapting the geometry, the diameter, the mass, the boundary displacement limitation, the spring stiffnesses, and this in order to ensure the correct opening of the regulator, and also sizing the lower chamber in order to ensure the correct closing of the valve. And again, we calibrated the different parameter setup, again, the test data, which are introduced in our model, like we've done before for the other part of the systems. And then I come to the propellant tank. And for the propellant tank, so those propellant tanks account for the biggest part of the land vehicle mass. So it's around 11 tons when fully loaded. And we have here 4 tanks You see here again definition of the different fluid, but you see that we can also specify some spacecraft attitude and acceleration that could be applied to the tanks. And from the top, we have the boundary condition representing the helium pressure regulators with some latch valve and some downstream piping, modular piping, which come to the ullage of the propellant tanks in order to pressurize them. Below the tanks, you have the fuel and the oxidizer flowing through, again, different pipes and which are set to give some we set also some boundary conditions in terms of fuel and oxidizer mass flow rate in order to do the proper sizing of those piping. And in the middle, you have the tanks. And for the CAD model of the tanks, we build this with Simcenter 3D. So we simplify the design, which is based on some, again, open literature and somehow some good engineering judgment. And as such, of course, this model is not the real CAD, but it's, let's say, fairly representative of it. And we proceed by importing this, I would say, CAD file using some CAD import plugin feature we have in the Simcenter Amesim in order to, one, generate the shape and the other information files needed for the parameterization of the tanks. And also we generate the sketch with the tank penetration, the different orifices, and this feature allows to do the automatic parameterization and location of the different penetration of the tank. And this avoid also some, I would say, error entering directly those parameters by hand. And it also ensures that data consistency with the CAD. And at hand, when you assemble all those different subsystems, you obtain this global integrated model. And let me show you the results. This is our global model. Like indicating during my presentation, you can find this model as well as the previous one for the two-phase flow system in our demo portal. So we have a demo portal for the different, I would say, industry market, and for space, for the launcher, you find different examples and you find the different step I described to build a subsystem, and you find this global integrated model I will present now. And just to illustrate quickly this model, in order to help you to enter the different parameters, we have different apps. I will not describe them all, but for example, describing the geometry of the nozzle, we developed an apps which allow you to enter your own user profiles, which describe the geometry of the nozzle. So here I just enter a nozzle radius as a function of the length of the nozzle. So this is a simple two-dimensional table that I refer. And I also, because I have a regenerative circuit, for instance, define different heat exchange area zone that are represented here by the orange and blue area, and giving some position for the thermal nodes in my systems. I can discretize my nozzle, so in two zones, and with these apps, you can automatically compute what is the surface of heat, which is used to compute the heat transfer between the nozzle and the cooling jacket, for instance. We have again for or valve assembly some interesting applications which are built on top of the component and which help to understand a bit the influence of the different parameter. Sorry, I need to resize. Here, for example, for the valve, you see that you can change, for example, the spool diameter, the rod diameter. You can change also the flow area as a function of the displacement. And when you change a value in this application, automatically, for example, on the left, you have an adaptation of the graph, which allow to validate, for example, your design. And when you refine your design and when you run simulations, you obtain and you can compare again with the test data we import from the literatures. So I kept some plot. You can compare the performance of your simulation model with the test. So if I go directly, for example, to the thrust, you see that here we can compare the thrust obtained by the simulation and the RAN referenced by the test, and assay the discrepancy. You have also here also the specific impulse. I think the real value for the Aristus is around 325 for second. You can check then the evolution of the combustion of the pressure in the combustion chamber. You can also check the regulation of the mass rate for the oxidizer and the fuel, and so on. And you can then play different scenario. And for instance, here in our simulation, in the Aristus engine, you have some part of the radiation of the regenerative circuit, which helps to warm the helium and somehow maintain a pressure in the helium tank. And you can follow what is the evolution of the radiative heat which is sent to the helium tank, and what is the impact on the tank temperature of the helium, and what is the impact on the pressure along the mission profile. Yeah, and I'm close to the end of my presentation. And so, as a conclusion, I show you different embedded tools we have, which helps to do the design and the parameterization of the different components. Obviously, system simulation allows you to size components and systems at early stage in order to reduce the cost and integration issues. As the model develop is dynamic, you can develop and also test your control strategy. And we saw that we can have some high fidelity plant model, for example, to simulate the valves or the linear actuators in order to be more predictive. And MSIM, as a collaborative comprehensive platform, allows you, like presented in my first topic, to do co-simulation with 3D simulation in order also to integrate some physical phenomena which might be difficult to capture with the system simulation, like the 3D radiations. Thank you. This is the end of my presentation, and maybe we have some minutes, times to take some questions. So Mason, if you want,
yeah, thank you for that.
Give you back the word. Yeah.
Yeah, if you have any questions, you can type into the chat, or you can type into the Q&A panel. I don't see any questions so far.
Yeah, maybe just a word, Mason, to say that those use cases I presented, we have different available materials that can be shared with the attendees. For the first use case on the mechanically pump loop system to cool down the electronics, My colleagues also recorded some presentation that can be shared afterwards. And of course, we remain available through direct email exchange if there are any specific questions about them.
Yeah, I would say that if you have any other questions after this webinar, just feel free to reach out to me and we can forward that questions. All right, I think it's getting pretty late at your time zone, so I think we can get this wrapped up. And if there's any other questions, we'll get this recorded and posted to YouTube. Feel free to reach out if you have any questions. But yeah, I think this is a wrap. Thank you. Thank you everyone for your time and participation.
Thank you.
All right. See you.